Alright, silly people, here's the situation. We're going to be checking the energy time uncertainty principle, uh, specifically for the wave function given in problem 2.5 in chapter 2, by calculating the uncertainty in energy, the uncertainty in position, and the time derivative of the expectation value of x exactly. So this is going to be a bit of a long one, I think. Mostly because this wave function is kind of chunky to deal with. And I'm going to write the time-dependent version of it now because I did calculate that in problem 2.5. I'm going to be cheating on using my own video from problem 2.5 back when I didn't know what a microphone was to get some of the useful results here. But that's the time-dependent version of it. And then we're going to be, just going through all of these steps bit by bit. So the uncertainty in energy, sigma h, is the square root of the uncertainty in h, or the expectation value of h squared, minus the squared expectation value of h. So I didn't calculate what either of those were in my 2.5 video, so let's do that now. It's the integral from 0 to a dx psi star h psi. So I'm going to write out what those are. Psi star is going to be, and then we're going to pick up a factor of 1/2 out here. It's psi 1 star e to the I e1 t over h bar plus psi 2 star e to the I e2 t over h bar times the Hamiltonian times psi 1 e to the minus I e1 t over h bar plus psi 2 e to the minus I e2 t over h bar. Right. So, cool thing about this is that the Hamiltonian acting on a stationary state for the infinite square well just gives back the energy value of the infinite square well. In fact, that's the case for like most stationary state problems, so this is just an eigenvalue equation. So I'm just going to copy the top line of that thing there. And then what's going to happen is we're going to pick up E1 on the psi 1 term and an E2 on the psi 2 term, which is reasonable to deal with. So this is times E1 psi 1 e to the minus I E1 t over h bar plus E2 psi 2 e to the minus I E2 t over h bar. Now, we're going to have to multiply these together. So I'm going to do a curly bracket here because there's going to be one term proportional to E1, that's just integral from 0 to a dx of the square modulus of psi 1 times nothing, plus there's going to be a E2 term, 0 to a dx of psi 2 squared with nothing attached to that. And then there's a couple of cross terms, so there's an E1 e to the minus I E1 t over h bar integral 0 from 0 to a dx. It's going to be psi 2 star psi 1, and then there's an E2 e to the minus I E2 t over h bar 0 to a dx psi 1 star E2, psi 2 anyway. But I shouldn't have bothered writing those out because those integrals are 0. Those stationary states are orthogonal to each other. And then the integrals of the square modulus of each stationary state are just 1. So we've got 1/2 of E1 plus E2. Right. I think it's not too hard to convince yourself at this point that the expectation value of h squared is going to be 1/2 of e1 squared plus e2 squared, just because you're changing out the operator that you're putting in between the wave functions with h squared. So you're just going to pick up additional factors of e1 and e2 in those. So I'm going to assume that's cool, and then keep going. So then sigma h is going to be the square root of 1/2 of e1 squared plus e2 squared minus 1/4 of e1 plus e2 squared. So just doing the squaring bit on the term on the right, we've got e1 squared plus e2 squared plus 2e1 e2, and then doing the subtraction, 1/2 minus 1/4 is 1/4, so we got 1/4 of e1 squared plus e2 squared minus 2e1 e2, right? So that's e1 plus e1 minus e2 squared times 1/4 and a square root, so it's just 1/2 times e1 minus e2. That wasn't too bad. The next part is too bad. So we need sigma x, which is the expectation value of x squared minus the squared expectation value of x. And I've already calculated expectation value of x in my video for problem 2.5. I'm going to write it out here. T over 9 pi squared. But I haven't calculated what the expectation value of x squared is, so I think that's what we're going to spend the bulk of this video doing. That's going to be expectation value of x squared is integral from 0 to a dx of x squared square modulus of psi. And also I already know what the square modulus of psi is in terms of like the actual functions, also from that video. So we're doing a lot of stealing from that video. But splitting up the integral, it'll be 0 to a dx x squared sine squared pi x over a plus integral 0 to a dx dx x squared sine squared of 2 pi x over a plus 2 cosine 3 omega t integral 0 to a dx x squared sine pi x over a times sine 2 pi x over a. So a lot of terms, a lot of integrals that we have to do, but I'm going to try and get to a point to show you that like all these integrals are actually the same integral, using trig identities. So sine squared of anything is just 1 minus or 1/2, so I'm going to pick up a factor of 1/2 out here. 1 minus cosine of twice the argument, so 2 pi x over a here. We got plus 1/2 integral 0 to a dx x squared 1 minus cosine 4 pi x over a. Okay. Plus 2 cosine 3 omega t, and actually I'm going to get rid of that plus 2 just because we're going to apply a similar style trig identity to the pair of sine functions there. It starts out with a factor of 1/2, but then it gets into cosine of this argument minus this argument, so minus pi x over a. and then minus cosine of this argument plus this argument, so 3 pi x over a, right? So just adding up the integrals now, I guess. We've got two factors of the integral that is just x squared. So 1 over a, 0 to a dx x squared. Two factors of that times 1/2 makes 1. Minus the integral cosine, it's 1/2 the integral dx x squared cosine 2 pi x over a minus 1/2 integral dx cosine 4 pi x over a. I'm gonna stop writing the bounds just because you guys know that the bound is 0 to a. It's the infinite square wave problem. And then plus cosine 3 omega t big bracket integral dx x squared cosine, and then cosine of a negative argument is the same as the cosine of a positive argument. So positive pi x over a in there, minus, and then that also has to have, no, that's fine. Integral dx x squared cosine 3 pi x over a. Close big bracket, close square bracket. So there's really just two kinds of integrals here. There's the integral of x squared, which is incredibly easy. And then there's the integral of the x squared cosine stuff. So I'm going to try and do all those integrals at once by doing a general integral here of integral dx x squared cosine n pi x over a. Right, so I'm just going to do u equal, I'm doing integration by parts now. That's the only way to do this integral, I think. U equals x squared, so du is 2x dx, and so dv is cosine of n pi x over a dx, and then v will be a over n pi cosine, or no, it'll be sine now, sine n pi x over a. Right. So I'm going to then just say this is going to be equal to uv, so ax squared over n pi sine n pi x over a evaluated from 0 to a minus integral dx. It'll be more complicated than that. It's minus 2a over n pi integral dx x sine of n pi x over a. Right. So I'm going to do integration by parts again to do the inner integral there. So this time u is x, du is dx, dv is sine of n pi x over a, dx v is going to be then minus a over n pi cosine of n pi x over a. Ugh. I'm trying to write fast, but I'm also don't want to be sloppy. And then, yeah, plugging that in then to the integration by parts formula, and also evaluating the outside term from 0 to a. We've got a cubed over n pi sine of n pi, which is 0. Sine of n pi is 0. Minus 2a over n pi. I should have done this in curly bracket, but whatever. Times uv, so negative ax over n pi cosine of n pi x over a plus a over n pi integral dx cosine n pi x over a. Okay? And then I have to evaluate this from 0 to a. So minus 2a over n pi, curly bracket, minus just a squared over n pi, cosine of n pi, plus a over n pi, and then that integral is just a over n pi sine n pi x over a from 0 to a. But this goes to 0 as well, because again, sine of n pi is 0. Picking up the two negative signs, it's going to be 2a cubed over n pi squared cosine of n pi. And then cosine of n pi is equivalent to, minus 1 to the n. So we got there. We have a table integral now for this kind of integral that shows up so much in our problem. So we're going to come back up here and use it a bunch of times. Okay, I copied it back down so I can quickly reference it. So 1 over a on the outside of the big curly bracket. Trivial integral, the result is a cubed over 3. Then we got minus 1/2 of 2a cubed over 2 pi squared with a minus 1 to the just 2. Okay. Minus 1/2 2a cubed over 4 pi squared minus 1 to the 4 plus cosine 3 omega t open bracket 2a cubed over 1 pi squared minus 2, and then times minus 1 to the 1 minus 2a cubed over 3 pi squared times minus 1 to the 3. Close bracket, close curly bracket. So it's pretty clear now that everything has a factor of a cubed inside of the curly bracket, so I'm going to factor that out. So I've got a squared over 3 minus 2a cubed over, it would be 8 pi squared minus, or no, it wouldn't be 8 pi squared, it would be 4 pi squared. Minus 2a cubed over 16 pi squared plus, I'm going to put the big brackets out front now, negative 2a cubed over pi squared positive 2a cubed over 9 pi squared. Right, and then all of these a's should be squared actually, like I suggested. And then this is going to be not over 2 anymore for those ones. Okay, so just combining terms now. Let's do just a squared. Let's just do it like this. 4 pi squared plus 16 pi squared is 5 times 15. Yeah, it's 5a squared over 16 pi squared plus, and I cannot stress enough to not forget the time-dependent term, plus, and then this is actually minus 16 a squared over 9 pi squared? Yeah, because 9 times 2 is 18. Yeah. So, and that's times cosine 3 omega t. Gross. So that's the expectation value of x squared. Let's do sigma x finally. It'll be a squared over 3 minus 5a squared over 16 pi squared minus 16a squared over 9 pi squared cosine 3 omega t minus whatever the expectation value x squared is. So it's minus a squared over 4, 1 minus 32 cosine 3 omega t over 9 pi squared squared. Fun stuff. Everything here depends on a squared, so I'm going to factor out an a from the radical. Then I get 1/3 minus 5 over 16 pi squared minus 16 over 9 pi squared cosine 3 omega t minus 1/4, and I'm going to do the square, 1 plus whatever 32 squared is, cosine squared 3 omega t over 81 pi squared. Pi fourth, I misspoke. And then minus 64 cosine 3 omega t over 9 pi squared. Right. Now I'm going to move the 1/4 through. So I got the junk out here. This is leading to something that I'm excited about. So just watch your ass. It's minus 1/4 plus, and then 32 over 4, or 32 squared over 4 is the same as 32 over 2 squared. So minus 32 over 2 squared cos squared 3 omega t over 81 pi fourth plus 16 cosine 3 omega t over 9 pi squared. Gang, did you see what just happened? This term exactly cancels out this term. This is why math is really, really lame. But I'm going to keep going. So 1/3 minus 1/4 is 1/12. I got the minus 5/16 pi squared here. And then minus, it'll just be 16 squared times cosine squared over 81 pi fourth. I'm just going to call it 16 cosine 3 omega t over 9 pi squared all squared, and call it good. So that's sigma x. We also do need to calculate dx dt exactly. So that's d dt of a over 2 times 1 minus 32 cosine 3 omega t or 9 pi squared, right? So that time derivative is a over 2 times positive 32 times 3. So I'll make it 32 sine of 3 omega t times omega over 3 pi squared. That's how I'll put it. And then I'll let the over 2 do some work as well. So I'm going to call it 16 a omega sine 3 omega t over 3 pi squared. Okay, we've got all the bits now of the calculation that Griffiths set us out on doing. Now the cool part, delta E delta T is what we're trying to prove. That is greater than h bar over 2. Um, but delta E is just equal to sigma h, so we got that piece. Delta T is equal to just sigma x over time derivative of the expectation value of x. That's just one of those equations that came right before this problem. And so yeah, we're just going to do sigma h, sigma x over dx dt, and check that is greater than or equal to h bar over 2. So plugging in our expressions, sigma h, we got 1/2 e1 minus e2. Sigma x, we got a square root 1 over 12 minus 5 over 16 pi squared minus 16 cosine 3 omega t over 9 pi squared squared. Yeah, and then for over dx by dt, we got 16 a omega sine 3 omega t over 3 pi squared. So I see some cancellations happening. This is going to end up being dimensionless, which is cool, which means we're going to be able to put it into a computer to make sure it's greater than h bar over 2. So yeah, I'm going to move the 3 pi squared up top, as well as the 16 sine 3 omega t down here. So it's 32 sine 3 omega t. And I'm going to put in the energy eigenvalues for the infinite square well here. Those are E sub n equals n squared pi squared h bar squared over 2ma squared. So it's going to be just pi squared h bar squared over 2ma squared minus 4 pi squared h bar squared over 2ma squared. And I'm tired of writing this, so I'm going to call this quantity S times S. And then doing a little bit of more math in here, just doing this subtraction now, it's negative 3 pi squared h bar squared. Oh, and I forgot we haven't canceled out omega yet, so there's an omega on the bottom here and an omega on the bottom here. Yeah, over 2ma squared times s. And then in the problem 2.5, omega was defined to be, I think it was pi squared over, pi squared h bar over 2ma squared. That's what omega has been the whole time. So I'm going to sub that in right here. That's negative 3 times omega there. So it's 3 pi squared over omega times 32 times sine 3 omega t times just minus 3 omega times s. The omegas cancel out, and we have, I'm actually going to write it out now, minus 9 pi squared over 32 sine 3 omega t square root 1 over 12 minus, and then there's an extra h bar here. Since omega only includes 1 h bar, there's still 1 left over when we factor it out. h bar minus 5 over 16 pi squared minus 16 cosine 3 omega t over 9 pi squared squared. And we're seeing if that is going to be greater than or equal to h bar over 2. And I'm just going to cancel out a factor of h bar from both sides as well. So numerically, we'll be checking that this value is greater than or equal to 1/2. So, so I've got my Desmos window up. This quantity here, which represents the red line, is the equation that I just wrote out, except I subbed in x for t and w for omega, and then I just set a value for omega. Doesn't matter what it is. If I increase it or decrease it, all it does is widen or narrow the loops. But I also graphed y equals 1/2. And at every point along this line, looks like our quantity is greater than 1/2, which means the uncertainty principle for energy and time is true. What concerns me is that there's also a negative portion to this. I'm just going to assume that that's not physical and just care about this stuff up here. I don't know what all this junk down here means. I'm just a mathematician. So yeah, that should be plenty. All right.